Welcome to Catalyst, a program about people, ideas, issues, and conversations around them.
Welcome to Catalyst. I'm Doug Webster, your host of the STEM Education Series, A Renewed Culture of Innovation. STEM stands for Science, Technology, Engineering, and Mathematics. This series was developed to discuss key issues around strengthening STEM education, both here in Vermont and elsewhere in the United States. Today's episode is problem-based learning, bringing the real world into the classroom. My guest today is Dr. Nick Massa, professor of at the Springfield Technical Community College in Springfield, Massachusetts. Nick is the principal investigator for the National Science Foundation funded STEM problem-based learning project grant being administered by the New England Board of Higher Education. Welcome to the show, Nick.
Hi, Doug. Thanks for having me.
All right. What is problem-based learning?
Problem-based learning is an instructional method whereby students solve real-world problems collaboratively in small teams. And problem-based learning has been shown to help students not only develop content knowledge, but also problem-solving and critical thinking skills. It's been around since the 60s, used primarily in medical school education, originally developed up in Canada at McMaster University, and is recently become more and more prevalent in today's educational system in business, engineering, mathematics. And it's a really fascinating way to teach. It's different from traditional lecture-based methods.
Great, great. Now, it seems like problem-based learning has been around, for a long time in the back of textbooks. In a physics textbook, you go to the back of every chapter and you've got a problem to solve. What you're focusing on is around project-based learning. What is the difference between the problem-based learning process and project-based learning?
That's a question that gets asked all the time. Project-based learning and problem-based learning are very similar. There's a lot of overlap between them. But the main difference is that in problem-based learning, the problem itself drives the learning. Students come into a learning situation, learning environment, without being taught how to solve the problem first. So there's a natural inquiry process that takes place, and students are required to go out and seek out the knowledge and information to solve the problem. Comparing that to project-based learning, in project-based learning, the problems are much more structured. Not unlike the difference between real-world open-ended problems and the back of the textbooks problems that you just referred to, which have all of the parameters well defined. So in project-based learning, basically that's very similar to like a capstone project in an engineering program, for example. In the last year, you take all the information that you learned in the first 3 years, you synthesize that and apply that in solving an actual problem. But it's very confined. There's an end product. There's multiple solutions in problem-based learning. There's no one answer that is correct. And the intent of that is to stimulate curiosity in the student. And if you attach meaning to the learning, they're not just learning math for math's sake. They're learning it to solve an actual problem. It has the effect of motivating students to learn and teaching them how to learn. One of the problems that typical graduates of tech schools, high schools, colleges is that when they go into industry, they don't have those the ability to think on their feet. And we hear this all the time in our engineering program. It's like they have great technical knowledge, but when presented with a problem where some of the parameters are not defined, it's like having the deer in the headlight look. So in problem-based learning, you learn how to work around that. You try to identify what's known, what's not known, and you work students through the problem-solving process so that it becomes internalized. It's a lot more exciting for them. It makes learning real.
Now, what are the circumstances in an education environment where problem-based learning should be incorporated?
Well, you're talking to a PBL evangelist, so I think there's room for PBL in all of education across the board. Some cases it may be more structured, some cases it may be more open-ended, but the more you can bring the real world into the classroom, the better the learning will be, the more motivated students will be towards applying what they know.
Now, in what ways can it help to integrate education disciplines to reduce the silos that we have out there?
That's a great question. One of the nice things about real world problems, actual problems that exist in the real world, is that they're inherently interdisciplinary. There's not just, if you're designing a robotic system, it's not just electronics, it's not just mechanics. There's an integration of different fields. There's also ergonomics, and a lot of other influence that shapes and molds a solution to that particular problem. So, you do get a lot of different disciplines, crossing each other's paths, like it is in the real world. Usually problems are solved by teams of people. Everybody has an expertise in a certain area. Together, the combination of that knowledge is more effective than just one person.
Right. So it's not just engineering students
No.
will take this on. It's
no. I speak engineering because that's my background. But
Yeah.
I mean, this, like I said, this has been used in the medical schools and law school education, business school.
Yep. Great. Do you have some examples of problem-based learning you want to show us or talk about and then show us?
Sure. Well, I got involved in problem-based learning several years back, 8-9 years ago, when in trying to develop my own students' ability to think on their feet. We applied for a grant to the National Science Foundation to teach photonics technology. I run a photonics technology program at Springfield. And we received a grant to develop problem-based learning scenarios. And what we did was we said, what do companies really want? When you hire a graduate, what skills do they need to have? And the best way the team thought to teach that is to go out into companies and ask them directly, when you have a problem, how do you solve it? Who's involved? What resources are available to you? So in our first NSF project, we went out and we created 8 what we call PBL challenges. And they are complete real-world problems solved from beginning to end, and we reenacted the whole process of the company and the team of engineers and technicians, what they had to go through to solve this problem. And what we did is we put it into a multimedia form where we chunked it, and so that teachers can bring this into the classroom and actually engage students in their own, in those actual problems, and then feed the information on an as-needed basis. If they get stuck on a certain aspect, a little more information can be presented. And we've got, like I said, 8 that deal with laser technology, photonics technology, and we just have finished up another 6 that deal with STEM technologies with a focus on sustainable technologies. The reason for doing the problem-based learning challenges focused on sustainability is to try to capture that natural curiosity and passion of young kids, students, high school, to enter STEM careers. By looking at different problems that are encountered in the real world dealing with sustainability. For example, solar, wind power, water, environmental protection, consumer products, things that are the kids are aware of, and they're passionate about. Creating the problems around those particular technologies. We're hoping that the end product will be an increase in the number of students entering the STEM careers. And we have some samples of that we could show you.
Okay, great. Now, can you describe this particular project?
This particular project that is in its second year. I'm working right now on it's a 3-year National Science Foundation Advanced Technology Education, ATE project. It's called STEM PBL. And what it will, the goal of this is to develop 6 problem-based learning challenges that can be used by students. As a matter of fact, they're available on our website for anybody to use for free. But also do professional development for teachers, both secondary and post-secondary teachers from around the country. We had a workshop at Boston University last summer to orient people, acclimate them to the PBL process. But then we had a full year-long online course in which we had 31 teachers, roughly half high school, half college level, both 2- and 4-year, engaging for a year-long, encounter, and what we made them go through the same problems that the students would have to solve. In addition to that, we've also developed a pre-service teacher course at Central Connecticut State University for pre-service technology and engineering teachers, basically teaching them how to teach using problem-based learning and how to use our materials. And the hope there is that they will become acclimated to not only our materials, but hopefully in the future develop their own PBL problems that can be added to a library that can be accessible for teachers around the country.
Great. Do you want to show
Sure.
one particular project here?
Well, the website where all of these are located, here's the plug, www.pblprojects.org. It's hosted by the New England Board of Higher Education. And if you go to that website, we have not only the photonics PBL challenges, but also the STEM PBL challenges. In addition, we had some funding from several different organizations to come up with a how-to video. We have a teacher implementation guide, and these are also aligned to national technological standards so that they can be used in the secondary schools. So if you go to the website, there are a number of different challenges, and I picked one that I thought would be kind of interesting to show you today. One of the companies that we worked with is a wind turbine company called Flow Design. And the reason we picked that is the company likes to use engineering students from local schools, actually high school and college level students, to come in and help them solve problems. And you'll see that when I show you the video. But each one of our PBL challenges, when you go to the website, has 6 sections to each. There are 6 sections to each. I'm trying to think of a slide, I guess, we show an organizational overview. I'm sorry, an introduction to the technology, where we kind of give an overview of what the field's all about. What is wind power, for example? Then we give an organizational overview to give students kind of a glimpse into the company or the organization that actually solved the problem. Then we present the problem statement, which is, and when we did this, we asked the company folks to present the problem the same way they first encountered it. We also recorded their brainstorming session that their people went through to solve the problem, and then the problem solution. One of the things that differs in our approach to PBL is that a lot of it, I mean, there are some materials out there, but most of them don't have solutions to them that teachers and students can actually go back and compare and contrast their own students' solutions with. So it gives them a little bit of closure at the end of the process. But I'd like to key up the introduction to Flow Design now.
Okay, well let's go ahead and take a look at that.
One of the great challenges of the 21st century is to produce the energy we need while minimizing harm to the global environment. As the world's demand for energy continues to rise, it is important to develop local and renewable energy sources such as solar, hydro, wind, geothermal, and biomass. Wind power is one of the fastest growing renewable energy sources because it uses a free, locally available, and inexhaustible fuel, the wind, and it produces no harmful emissions. Although the idea of wind power has overwhelming public support, many people do not want huge, unsightly towers located near their homes and businesses. Noise and danger to flying birds are also concerns associated with conventional wind turbines. But what if a smaller, more efficient wind turbine could be developed that could be used in residential areas as well as on large wind farms? What problems would need to be solved to make quiet, convenient wind power a reality?
So in that video, you saw just, what is wind power all about? What are the hazards of the larger turbines? Why this company is developing these smaller turbines? And that kind of sets the stage for the problem. The next segment gives you an overview of the actual company that did this and the school that they collaborated with. So if we can look at the organizational overview.
Flow Design Incorporated, located in Wilbraham, Massachusetts, is a research and development company that utilizes state-of-the-art aerospace technologies to develop, prototype, patent, and market new products. Since 1990, Flow Design has successfully developed products for companies such as Sikorsky Aircraft, Rolls-Royce, and others. The Flow Design Wind Turbine Corporation is a spin-off from the parent company. Its mission is to develop, fabricate, and test a novel mixer-ejector wind turbine that uses an innovative shrouded design to draw more wind flow into the machine. The new design can potentially generate over 3 to 4 times the useful energy compared to a similarly sized conventional wind turbine. Working with faculty and students from the engineering department of Western New England College in Springfield, Massachusetts, plus its unique aerospace technology, allows Flow Design to be innovative, comprehensive, and efficient.
So now you see where the company is and its proximity to the local college.
Okay.
The next segment that is shown is the actual problem statement. And again, when we went into these companies, we asked them to present the problem, exactly how they had originally encountered the problem. So if you can key up the problem statement.
As you know, we have a novel design for a wind turbine using a smaller footprint than your typical prop blade turbine. Because the props are so big, they spin slowly so they don't break apart. They use large gearboxes to extract energy from the wind. Our design, on the other hand, is smaller and rotates much faster, so we can explore multiple means of converting mechanical energy to electrical energy.
I saw a wind farm out in California. Those turbines were huge. Are yours as big?
No, they're only about 10 feet in diameter. A typical turbine is about 150 feet in diameter.
Wind power is really cool, but aren't there environmental dangers?
Yeah, like killing birds.
We've conducted studies that show that our turbines are safer because they're much smaller and they're quieter too.
Wow, that's cool. How can we help?
Well, it seems to me that we have a unique opportunity to simplify our turbine design to make them more efficient and reliable. We're looking for innovative ideas, and we'd like you to develop some new concepts for extracting energy from a wind turbine.
When do you need this by?
We need a working model in 3 months. Remember that your design needs to be simple, efficient, and cost-effective.
In that segment, what you saw is an engineering manager explaining to his staff, a couple of them were actually engineering students, that we have this new novel design. We need to figure out how do we get the energy out of this, which is really a kind of a cool problem from an engineering standpoint. You can tell there's limited information there. And I've given these problems to my own students, and they stop for a minute and go, well, there's not enough information. It's like, exactly, there never is. So that creates a curiosity. After the deer in the headlights look goes away, then they say, all right, what do we do? And built into each one of these challenges, and this is really the cool part of these, is something called a problem solver's toolbox. And what this problem solver's toolbox does is it walks students through the problem solving cycle. And we implement this in a 4-piece segment that is recursive, and it starts out with problem analysis, where students collectively sit back and analyze the problem. What do we know? What's missing? What do we need to learn? Are there any constraints? So basically framing the problem, which is really one of the hardest parts of problem solving in general. Then the students go into self-directed learning, where they break up the task of what needs to be learned into the group. And they all go out and they do their independent research, and we have tools to guide them through that whole process. The tools are called the whiteboards, by the way. They were kind of inspired by House, MD. I don't know if you've ever seen that show.
Yeah, oh, sure.
But they go up on the whiteboard and they list out what they know, what they don't know, what their learning goals are. Then they regroup, they come back, have a brainstorming session where they present all of their newly learned knowledge. And the whole idea here is to take new information and build upon prior knowledge in a way that's done collectively, and then test that idea out. Now, the solution may work, it may not, and if it doesn't, they just kind of keep going through the whole process. So they're teaching them a cyclical learning process that they can apply to any problem, really. And that's really the focus of what we're doing.
Okay.
The next segment, once students get to a certain point and they kind of hit a brick wall, they've gone as far as they can, the instructor has access to the brainstorming session that the company went through. And these are password protected, so teachers can feed them on an as-needed basis, because they're all online, so we had to figure out a way to protect them from having students kind of jump in there. But if you can queue up the problem discussion, these are some ideas, kind of the hints that that the team went through.
Okay.
Okay, what do we know?
I did some research. Here's how those big conventional wind turbines work. First, wind turns the rotors, but they turn pretty slowly, so a gearbox increases the rotation speed. Kind of like the gears on your bike.
Why do you need to increase the rotation speed?
The faster the generator turns, the more electricity you get. It's the Faraday effect. Duh.
Why don't we just design a simple gear system and attach it to a generator?
Okay, I have CAD experience, so I'll do the design. Then you guys can take it to the rapid prototyping lab and build a working model. Then we can check it out and see how it works.
Let's take a look. What do you think?
There's a lot of moving parts. What happens if one of the gears breaks?
The gear is making it pretty unreliable. I don't think this is all that innovative either. This is what they're already doing now, right? There's got to be a better way.
Wait a minute, why can't the turbine itself be a generator?
And that's the hint, so they go through, they start talking about Faraday's law, which is really a backdoor way of getting them to learn about electromagnetics. But they give some hints about, the strategy that they took. Doesn't necessarily mean students have to use their method. But the whole idea in the flow design problem is that the generator itself, because of its unique design and the fact that it spins faster, can actually be used or transformed into a generator itself. So once students work through the problem, they come up with their own solutions. The idea is for the students to present as a group, as a team, their solution to the class. And every team goes through presenting their solutions. And then it opens up the floor to a compare and contrast session where the flow design, the company solution is then shown, and then the instructor can lead them through a very meaningful discussion about what was learned. Why did you guys do it this way? Why did you guys do it that way? What differences are there? What did you learn? Was your design better? So the solution we can look at now. Yeah. This is the actual solution that Flow Design came up with. Actually, the students came up with.
So let's see what you've come up with.
So we thought about Chase's idea of turning the wind turbine into an electrical generator without having to use a gearbox or any other moving parts.
We looked up how an electrical generator works, and it turns out that it's pretty simple, just a permanent magnet moving over a coil of wire. When a wire moves through a magnetic field, it causes an electrical current to flow. The current can be used to charge a battery or even be connected back into the electrical grid.
In the generator, a set of rotating magnets is arranged so that their polarities alternate between north and south. They are placed on a rotating shaft called a rotor. Then, a bunch of coils of wire are mounted in some kind of housing around the rotor. The housing is called the stator. When the rotor turns, either by wind, hydro, or steam, or some other means, the magnets passing over the coil create an alternating current.
In most large prop-type wind turbines, the props turn too slowly to be directly connected to an electrical generator, so they use a gearbox to increase the rotational speed.
Yeah, and that costs more money, and the moving mechanical parts can wear down.
Our idea was to attach permanent magnets to the turbine blades and mount coils of wire to the shroud. We turned the whole turbine into a generator.
So how fast does the rotor need to spin?
Well, we did some research and determined that for our prototype, we needed a rotational speed of about 66 RPMs.
How many coils and magnets do you need?
So in general, the more magnets and coils you have, and the smaller the air gap between the magnets and the coils, the greater the power generated. Our model is small, so we're only able to fit 60 coils and 60 magnets to create a two-phase AC system.
We tested our model and found that the output voltage generated was about 5.7 volts with a current of 1 amp. This translates into a power rating of 5.7 watts.
Well done, team. I think Flow Design will be very pleased with your work.
Okay, now whose idea was that? You initially said it was Flow Design, but I don't know if they got that.
Students at Western New England College, which is actually now Western New England University as of last week officially, but those are students from the engineering program, the mechanical engineering program there.
Okay,
and Flow Design does this all the time. They work with Western New England, with Olin University, and several other, UMass, I think UConn, trying to get students in as interns to do a lot of the problem solving for them.
Okay. Now, what are some other projects or problems?
Problem, yeah. Okay. In the STEM PBL project, so that's one of them.
Yeah.
We have one that we worked on with a company called SPG Solar in Tucson, Arizona. In that particular problem, they have an old building that needs to be retrofitted with solar panels, and the problem is the building is not designed to handle the weight of traditional solar panels, so students are tasked with finding an alternative solution to add solar power, but also limit the amount of weight. We worked with the Cranberry Growers Association of Cape Cod, the Ocean Spray commercial. Yeah. Basically, we found an organization or a cranberry bog owner who wanted to redesign an old dead cranberry bog to be more environmentally responsible, to limit or eliminate the runoff of pesticides and chemicals, which is really kind of neat. And these problems, while they may sound advanced and sophisticated, they can be solved, at high school and college level.
Right. Right.
I mean, the flow design one, for example, can, just conceptually, there's lots of different ways you can do that.
Okay.
We also worked with Johnson & Johnson on another project that uses green chemistry in consumer products. Basically, when you wash the shampoo out of your hair, you don't want it to go down the drain.
Now, where do you see the whole project going?
Well,
like
hopefully
over the next 5 years or so.
We've gotten a tremendous amount of tremendous
in 30
response.
seconds.
Okay, tremendous response to the materials that we've developed. We're currently writing the next proposal to the National Science Foundation to continue our work and hopefully develop a center for problem-based learning. We could expand the reach and the scope of the work that we're doing. Because there are some other good projects out there that do problem-based learning also that we'd like to kind of put everything under one umbrella.
Great.
Just as in closing, I was at the American Society for Engineering Education conference last week.
On Vancouver.
And every year for the past 3 or 4 years I go, and I've seen a tremendous increase in the amount of problem-based learning being used in engineering education.
Yeah.
I think they finally got the picture that this is the way to go.
That's great.
And it is in my mind.
All right, well, good. Well, thank you so much, Nick, for coming up to Vermont
My pleasure.
to be on the show. We appreciate that.
All right.
And thank you for joining us.
My pleasure.